Hello, welcome back to our part 8 video. We're going to split our part 8 video into two parts. We're going to have the first part, which is this one, which is just about the content of part 8. We're going to have another one afterwards which covers the annex of part 8, which is to do with the calculations needed for barycenter calculations and energy assessment checking. So we're going to split this one into two parts. There's going to be a lot of content, but we're just going to kind of keep it moving fast. We don't want to go too deep into it yet, because again, this is all potentially going to be subject to change. It may not even be in the regulations when it's released. So first question is why do we need an 8th part? Over the 10-15 years or so, we've had a lot more introduction to low energy requirements with proof document L in the building regulations, changing of our light switches to even putting stickers on light switches to switch off lights, changing our lights from incandescence to low energy. So we've been making changes already, but there's nothing in the wiring regulations that's said to do that. That's now what's going to happen. When you look at the content that's here, a lot of it we kind of already do. So the IT are actually saying this. It's not out of the ordinary, and it's not a problem. They also state that here it's still fundamental principles of the regulations to maintain the safety of persons and property and livestock. The actual energy is kind of like a curveball. It's a consideration, but it's not the main driving force of the regulations. It's also mentioning that the like all British standards, it's not statutory still, and with regards to the requirements of section 801, it's not actually safety related, and so it doesn't sit conventionally under the electricity at work regulations. It's going to sit more under the building regulations with the proof document L for the conservation of fuel and power. But again, if you've done building regulations study, you'll know this, and you'll be like, yeah, a lot of this stuff we've done because of proof document L. There's 4 of them there: dwellings, non-dwellings, new, not new, and stuff. Yeah, that has stated the changes over many years now that we should have on our installations, and we've been putting them into practice quite often. Also, we've got in Europe significant changes in other European countries. France just this week have announced that they're going to stop manufacturing or allowing the manufacture of petrol and diesel cars after 2040. A manufacturer has actually also stated that they won't make any more after 2019. This is all to do with the requirement of the European 28 or whatever it is to actually achieve a lower carbon emission and improve the footprint to a certain period. But it's interesting when you see how the rest of the world is doing compared to Europe. Europe's doing quite well compared to a lot of Asia and a lot of the US. But yeah, so it's not like it's a change of direction, a change of work. It's more a case of that thing you've done all this time, we're now telling you that you should have done that kind of thing. There are a couple of new bits, new thought processes, the barycenter for example, but we're going to cover those as we go through. Alright, so the scope of the part 8, this is actually from the draft now. So 801.1, it provides additional requirements, measures and recommendations for the design and erection of all types of installation, including local production and storage of energy for the overall efficient use of electricity. It introduces requirements and recommendations for the design of an installation within the framework of an energy efficiency management approach. So, an energy efficiency management approach. The problem with that is industrial, commercial. We have certain considerations. LED lighting. We have considerations with using renewable technologies, but one of the main concerns is we also consider cost. And an example of the changes that are under consideration now is things like cable sizes. When we have our cable size, when we do our cable exercises, we normally say, right, let's try to calculate them to be as small a cable as possible to save the money. So we make sure that we size it for thermal effect, so it's heating under load, it's not going to create a fire, and we save money that way. But what it's now suggesting is, well, what if we do that calculation but then increase the cable anyway to allow a lower thermal effect? Because again, if you create heat under normal load, that heat is going to be given off as a wasted energy. We want to avoid losing any kind of energy. That's the whole point of energy efficiency. So one of the recommendations now is going to be to consider increasing cable sizes beyond the calculated ones for energy efficiency. That's going to have a knock-on effect with cable selection and all of that stuff. But this is the kind of attitude that's being put here. That's what the barycenter method is all about, putting the actual supply and distribution centrally to actually make the runs of distribution as short as practicable, to obviously prevent any thermal effects and load shedding. But we'll see where this goes. Alright, the recommendations apply within the scope of this part for new and for modifications. Okay, it doesn't apply to products. Alright, well that's understandable, you know. So products will have equipment manufacturing standards. It also does mention that installations with very small loads and short cable lengths, such as dwellings, should probably not be considered here because of the calculations suggested might not be practicable. But again, if you comply with L1A or L1B and the equipment selected is of a energy performance characteristic, then that's kind of all that you can do. You're not going to start putting in like ridiculously large cables for short runs and low power demands. That's not going to happen with domestics. So there is an ability to exclude domestics from this. Okay, so fundamental principle here: safety. Yeah, the safety of persons, property, and livestock remain the prime importance. Okay. Active electrical energy measures shall not impair the passive energy efficiency measures of the building. Okay, so the passive energy efficient measures is where you've got obviously like a building structure or a building category. You've got illustrated here. You've got adopt basic measures of low consumption devices, thermal insulation, power factor correction. So those they're like the primary measures. When we can actually add additional measures, we can have active energy efficiency measures, control, monitoring, variable steel speed drives, etc., etc. But anything that we add as an active measure mustn't compromise a passive measure. Another thing, and this is interesting, is 801.412, availability of electrical energy under user decision. The efficiency management shall not reduce electrical availability and or services or operation below the level desired by the user. So if you decided to apply them with a low amount of power because of energy efficiency, the user shouldn't be penalized, or they should be able to draw the power that they need at the time. It shouldn't incapacitate the user. Good example of this is in large warehouses when they walk around and they've got these sensors lighting up the lights. By the time that the actual lights have come on, quite often they've moved on. So they need to light up in the areas that their users are going into, as well as where they've just been. So I've seen this in many factories and warehouses where they've done this energy efficiency movement. All well and good, but the user shouldn't be compromising the ability to safely work for the sake of energy efficiency. And now they've got this regulation, that's something I can actually pick up on EICRs, for example, because I've often mentioned that people walking around don't have sufficient light to freely move. We've got 801.413 design recommendations. The design principles included in this part will take into account the following. We've got load energy profiling, which we'll cover in a minute. Availability of local generation, solar, wind, generator, etc. Reduction of energy losses. The arrangement of the circuits with regard to energy efficiencies or meshes. Meshes is how they group certain parts of an installation, such as air handling units or power, where we can just say, right, well that's a large power, so that's a mesh, this is a low power, and you can obviously break it up into chunks that way. The use of energy according to the customer's demand, and the tariff structure offered by the supplier of the energy without losing the quality of service and the performance of the installation. Alright, sectors of activities. For a general approach to energy efficiency, 4 sectors are identified. So we've got residential, or buildings, dwellings, commercial, industrial, and infrastructure. And these have to be recognised separately because they have different characteristics. For example, with residential, we've already mentioned that the complicated scope isn't really needed here. So a proof document L will tell us, no larger than X wattage external floodlights and X amount percentage of the luminaires must be X wattage and all this stuff. When you think about other places, industrial locations, there's quite a heavy duty of care to have a safe system, but quite often there's money to be saved by having energy efficiency. So there's time and there's investment. Many places I've done work with, they've done refurbishments where they have variable speed drives, they have BMS systems, they have obviously sensors on the lighting, so that's great. Commercial, the thing about commercial is sometimes there's little care for conservation of energy or measurement. Often residents will be on short-term leases, or there is perception that although they provide or they build for the energy that they're using, because of the short term of their lease, they're obviously not going to be there forever to invest, or maybe they feel powerless to actually make any changes because of their lease. So a lot of commercial buildings may suffer from this. With regards to infrastructure, you've got things like street lighting, highways and transport. Again, lots of infrastructure these days has little solar panels powering it up, but so there are separate sectors that need to be considered under this. Design requirements and recommendations 801.6. Design principle of the installation shall take into account the load energy profile, active and passive, the minimization of energy losses in the system by means of optimal location of the transformer, local production and switchboard or barycenter. So the HV to LV transformer, the supply needs to come in to as close a practical location, and then the sub distribution needs to be as short as it can be. A location of the substation and reduction of losses in wiring. Losses in wiring are losses of energy. Now, we've often considered them as losses that have just been financially lost, but now to think of them as energy losses and try to avoid these losses. With regards to load profiles, you've got the main load demands within the installation will be determined. The loads in kVA, together with a duration of operation and or an estimate of the annual load consumption, should be identified and clearly recorded in the user documentation. Think about your heating. You've got the old off-peak heating, so that's an example of a separate profile. Okay, so you can have different classes of profile. We can have a low profile for a domestic. We can have a low profile. I've actually got another slide of it exampled here. So we can have a class 1, which is domestic unrestricted, class 2, which is domestic economy 7, where it's on a lower tariff. What we do then is we use equipment that will actually use the supply out of hours, which is better on the network, and will store the energy. These are examples of load profiling. In the industrial or commercial, another example of load profiling is where we would mesh the circuits into unique, segregate them to unique meshes. And what we then do is, let's say you have a lighting circuit in a factory. You'd normally put the lighting circuit on 2 or 3 circuits. One of those circuits may be best for the outer circle or the outer edge circuit, because if you've got daylight coming in, what you want to do is have a recognition that the lights that are there that don't need to be on in the daytime due to borrowed light from the sun, we can actually say, well, that is a different profile, and so that can be controlled or just switched off and only turned on at night time. For example, all this is load profiling. It's recognizing parts of the system need levels of illuminance that are larger than others, and so we say, right, well, let's switch those lights on a sensor. Let's turn those lights on a switch that's only used at night time. This is all examples of load profiling. We also have account taken of the building's use, construction and space available for the best position of the transformer and LV switchboards. So, couple of notes. It should be determined with the building's designer and owners prior to construction. So before they build it, it needs to be determined where the best place for distribution is. The barycenter method is one solution which identifies if the load distribution is uniform or a localized type and determines the total load barycenter location. You can Google what barycenter is about, but it's all about something spinning around the center point. We want to have our intake in the middle so that the distribution circuits go out to the same length. If we had the distribution on the corner, then the distribution to the furthest corner would be long and there'd be losses. So we want to have is our distribution in the center as best as we can. So the barycenter calculation here is where you consider it on an axis. So you have an x-axis and a y-axis. You can also have a 3D one which includes a z-axis, and what you do is you calculate considering you need power there and power there and power there and power there. You look at all of their power demands and you look at the distances from each other, and there's a long calculation, which is the sum calculation here, where you work out the ideal position for your distribution. This is going to be included and discussed in the next video, so I'll go through the examples in the book in our part 2, part 8 video. The HV-LV substation. To find the optimal solution for the transformer, consideration of the following will be taken: the number of substations, the working point of a transformer, and the efficiency of a transformer. We've also got, again, most of this might be done by the actual building company. We've got optimal number of substations. So depending on several criteria such as the required power, the building surface area, the load distribution, the number of substations and distribution layout will have an influence on the lengths of the cables. So this is all again about shortening it to make sure that the length can be short and the sizes are large to reduce losses. Let's mention the barycenter method again. Working point: the maximum efficiency of the transformer is when the iron and copper losses are equal. So there's discussion there on how to achieve full efficiency of a transformer. Usually the maximum efficiency to a network distribution transformer corresponds to about 50% of the maximum power rating of the transformer, and the maximum efficiency of the power transformer is when the load is near 100% of its rating. This again is a good thing for design, because we need to try to achieve full efficiency of our transformers, because that's going to reduce losses. Consideration will be given to the efficiency of the transformer, which are inherently efficient electrical machines. The environmental impact may depend on the energy losses, which depends on the working point. Okay. Couple not used: efficiency of local procedures for substations and efficiency of local storage for substations. They are not used. We're still in HO16, which is your design there. You've got losses for volt drop now. HO1.6.4.7.1. These regulation numbers are long. Consideration will be given to limit the volt drop within an installation to the level below that required by 525. Again, we've been doing that. Something that we may start doing though is obviously finding with the maximum volt drop, getting the next cable, and then maybe just going up again, going up in size to minimize these cable losses. Cross-sectional area. Increasing the cross-sectional area of a conductor will reduce the power loss. This decision shall be made by assessing the savings within a time scale against the additional cost due to this oversize. Power factor. Consideration will be given to improve the supply's power factor to reduce the thermal losses in the wiring. Power factor correction is nothing new. Same as harmonics. Now, we've compensated for harmonics with more LED lighting and stuff. We've got to make sure that the equipment has either it's harmonic free or it has power factor correction, which will help with the harmonics. But we've got to consider reducing our harmonic content as best we can. Harmonic filters or whatever. Alright, 8017, determination of the zones, usage and meshes. The installation will be divided into zones for the purpose of energy efficiency. A zone represents a floor area in meters square or a location where electricity is used. Identification of these zones is needed to enable correct determination of the meshes. Okay, so they may correspond to an industrial workshop, floor in a building, a space near windows, or a space far from windows. Okay, so if you've got a factory with an administrative location and you've got a factory with a large powerful equipment location, then those are straight off going to be two separate meshes. If you've got, there it says a space near windows, a space far from windows, that's to do with your lighting. So nearer the windows will be one mesh and far from will be another, because they want to work independently of each other, these meshes, so we can have the ones nearer the window off more, so the daylight will do the job. A room in a dwelling, highway, road lighting, or a hotel kitchen. You get the idea. These are characteristics where there's a changing in power demand from one point to another. It could be a specific piece of equipment or a location. When you do your initial design, you'll decide that, and then they take them into these meshes, and we're going to assess the energy efficiency of those according to their meshes as well. Determining the usage within these zones. The use of particular circuit or zone shall be identified to enable accurate measurement and an analysis of its energy consumption. Okay, so this is where we're going to use a lot of energy for a certain task. Hot water production. Again, maybe we can put that on a off-peak tariff. Yeah, HVAC, lighting, motors, appliances. Determining these meshes. The installation will be divided into meshes. A mesh is a circuit or a group of circuits with respective current rating, etc. It can belong to one or several zones. A mesh can determine one of several usages. They'll be managed to use electrical energy to always fulfill the need, so there'll always be the need for the demand, taking into account factors such as the availability of daylight, the occupation of a room, the availability of energy, external temperature, other aspects linked to building construction, and passive energy efficiency. So again, lux levels, illuminance levels, occupation of the room, having a room that's not occupied, heating turned off, is occupied, lights on a sensor, kind of things like that. The determination of meshes in the installation will be defined so that they deliver the associated usage while allowing effective management of the consumption of energy in consideration of at least one of the criteria defined in the regs. Okay, so yeah, you might have a location where the heating is on certain timer controls, but you still need to have the ability for the users to demand. So if you think about a heater that's heating, it's on a timer, you can just hit the boost button, for example, then that can overrule the existing setup. These are all examples of how we create zones on our systems, or we put them into meshes. Criteria for considering meshes. Technical criteria based on external parameters such as time, illuminance, temperature. Interruption of certain services or applications shall be avoided during certain periods of time. The designer should agree on a daily, weekly, monthly or yearly scheduling for when some services or applications shall be available or can be reduced or stopped. Identifying these applications and gathering them in a mesh are key for an energy efficiency point of view. For example, defining a mesh for luminaires near windows and the second one for luminaires near the walls allows for switching off those near the windows when daylight is sufficient. Yep. Meshes. Electrical management for energy efficiency is a system approach aiming to optimize the management of energy use for a specific service with a defined electrical mesh. Take into account all necessary information concerning the technical and economic approaches. It is seldom that the optimum of a system equals the sum of the optimal of each part of the system. It is therefore necessary to consider the most appropriate meshes of the electrical installation from the electrical energy efficiency point of view. It's repeating itself really now. Introducing equipment or functions for reducing, measuring, optimizing and monitoring energy consumption or any other use aiming to improve the use of electricity may increase the energy consumption in some parts of a system. So it's interesting. So introducing equipment that has a function to reduce, measure or optimize the energy consumption can actually increase the consumption. Okay, for example, the use of a control device such as a thermostat, an electric heating system or a human presence detector and electric lighting system may increase the instant or global consumption of particular equipment for some devices but decrease the total consumption of the whole mesh. Impacts on distribution system. Energy efficiency will be considered in the design of the distribution system of the electrical installation, including the impact of different load demands, usage, zones and meshes. And 8018, energy efficiency and load management system. Requirements for the user. Requirements from the user are the first input to take into consideration. These requirements will be the key input to design the energy efficiency management system. Again, when you're going to do a design of an electrical system, you need to understand how the client or the user is planning on using the system. How, what daylight hours are they going to be doing the work in? What's the occupancy? And this is something that will need to be re-evaluated. So it might be that we have to start considering doing a let's say you have a building that's been running for 5 to 10 years. The building may have changed user, changed occupancy, changed demand, changed layout. It might be that a redesign needs to be considered on a scheduled EICR, for example, to consider if there are any changes that can be done to improve energy efficiency, either by helping with by introducing a mesh layout, changing the lighting, changing the switching, introducing power factor correction. Again, all stuff that we've probably done for the past 10 years or so now. Changing LED lighting, for example, introducing sensor switching. It's all stuff we've been doing. Energy efficiency and load management system. The requirement of the load. The designer and installer will take into account the user's decision on selection of energy efficiency appliances, such as freezers and lamps and things. The user may give priority to the usage of different loads as an input of the load optimization process for load shedding. The designer shall take into account the use of the installation in providing an energy efficient design. The manual override facility shall be provided to enable the user to take control from the automatic functions. Again, the user must be able to take control and use the system for their demand. This ensures safe working practices. Inputs from load, sensors and forecasts. Measurement, requirements on accuracy and measuring range, blah blah blah. Accuracy of measurement shall at least comply with the following. The meter at the origin of the loads will be accurate for billing purposes and can be used for the measurement of the efficiency of the whole installation. At a lower level, for example for some important meshes, it may be necessary to provide measurement with an accuracy allowing sub-billing within the same entity. For example, a company such as a hotel may wish to charge the department for catering separately from the department in charge of entertainment. Again, I mean, we've been able to do that already. We might put separate metering in for a landlord or for a business, separate metering in for a sublet office. Now they're saying, well, yeah, that's a good idea, but do that from energy efficiency's point of view for load management. Loads should be classified regarding their users' acceptance of load shedding. Some loads, such as IT equipment, computers, TV sets, are not suitable for load shedding. Some others, like heaters, fridges, electric vehicles, can accept without any impact on their service a shedding up to a certain period of time. So for each type of load, an acceptable time of shedding in normal conditions shall be determined. Note 1. As examples, the acceptable time for shedding for a desktop computer is 0 milliseconds, for a lamp is 50 milliseconds, for a fridge or a heater is 15 minutes. So the maximum time of shedding for each mesh is determined by the individual load with the lowest rated off time. For this reason, it is recommended to specify meshes that have loads with similar rated off times. Again, this is all about understanding the characteristics of the equipment and its demand. If it's going to be something that heats up, then the idea is to recognize that as a separate load to electrical equipment that doesn't pull significant demands. Again, if you're told by a customer what's going to use the most energy, what's going to use the most power, you're going to say that stuff that uses a lot of wattage. And that's what we're going to do here, is we're going to start recognizing them, and we're going to start creating either meshes. We're going to mesh them together, or we're going to give them separate identities to equipment that is of low energy efficiency. Energy sensors. Energy sensing devices shall be at least the same class as the energy performance and monitoring device. Forecasts. Forecasts shall be used as inputs to the energy efficiency management system, such as weather and occupancy forecasts. Data logging. Historical data, where available, shall be an input for making energy demand forecasts. With respect to the quality and effectiveness of the results and obtaining a high level of energy efficiency, all available data shall be taken into account. The energy management system for energy efficiency shall not impair communications for other purposes such as safety, control, or operation of device or equipment. Yeah. So they'll work like an auxiliary system, just separate. They won't stop or isolate equipment necessarily. Inputs from supplies, energy availability and pricing, smart metering. The user shall consider the information concerning the energy availability and pricing, which may vary with time. Where the supply is a local source, the user shall consider the minimum and or the maximum available power and define the price of this energy based on the total cost of ownership, including fixed and variable costs. Monitoring. The installation should be designed to enable the measurement of its total consumption in kilowatt hours for every hour of each day. This data and the related cost of energy information should be logged and stored for a minimum of 1 year and shall be accessible to the user. Again, for a user to make decisions, they've got to have data. I mean, we're seeing this with these smart meters now. This is what's happening with people, with dwellings. They're coming around putting in smart meters. Some putting them in well, some not so well, but it's now allowing users to see, if I put that kettle on, I'm now spending this much, which means I'm now using this much energy, and people are using that as a way to lower the amount of times that they use significantly high demanding pieces of equipment by allowing homeowners to see the amount of money that they're spending with the amount of power that they're using. It's having that effect of, okay, well, we'll use less, so we spend less, and that is energy efficiency as well. This is the same kind of idea here. Management of loads through the meshes. An energy efficiency management system comprises monitors for the whole smart electrical installation, including loads, local production and storage. It can manually, in easy cases, or automatically, in most situations, monitor the electrical installation of the smart electrical installation so as to optimize permanently the overall costs and consumption of the system. Take into account the user requirements and the input parameters coming from the grid, local electricity production and storage, the load sensors, forecasts, etc. If you've done any kind of power quality analysis or any kind of load studies, then you've probably done some of this already, really. But the idea of having meshes is to recognise, that part does this and that part does this, and it can allow users to make more suitable decisions about how regularly they use certain bits of equipment with their demand. Energy management system. The energy management system should be based on the end user's choice, energy monitoring, energy availability and costs, and inputs from loads, local electricity production and storage, energy sensors and forecasts. The energy management system shall include measurement of meshes, control, power quality, reporting, alarms, verification of good operation of the devices, tariff management, if any, security of data, display function for public awareness. Yeah. Multi-supply management, grid, local electricity production and storage. The overall power demand shall be optimized as far as possible as an aid to the overall energy reduction of the installation. Okay. Parameters for the implementation of efficiency measures. This regulation gives a requirement to the analysis or means the designer of an installation or facility manager has to use to determine efficiency measures and to achieve an energy efficiency performance level. The measures and levels are used to build the installation profile, or IP, and the electrical installation efficiency class. These requirements are organized into 3 topics, which are efficiency of current using or carrying equipment, efficiency of the electrical distribution system, installation of control, monitoring or supervision systems. Okay. So the efficiency measures for current using or carrying equipment. An AC induction motor can consume more energy than it actually needs, especially when operated at less than full load condition. This excess consumption of energy is dissipated by the motor in the form of heat, Idling cyclic, lightly loaded or oversized motors consume more power than necessary. A better choice of motor and motor control would improve the global energy efficiency of the electric motor system. Okay, so you can clearly say that they're looking at the types of motors here, the actual full loading of the motor, not having it going idle. Yeah. As about 95% of the operating cost of a motor comes from its electrical energy consumption, adopting a higher energy efficiency class according to the following. So, consideration will be given to the use of motor starters, motor control, device, variable speed drives. Again, I mean, this is stuff that we've used. Examples of aspects to be considered are reducing electrical energy consumption. Alright, consider using less. Okay. Optimizing the rated power. Reducing the inrush current. Reducing noise and vibration. In this way, avoiding mechanical damage and failures within the air conditioning or heating system. And better control. Okay. Know that in industry it's understood that 60% of consumed electricity is used to turn motors, and 63% of this energy is used for the application such as pumps and fans. Lighting. Lighting can represent a large amount of energy consumption in an installation depending upon the type of lamp and the luminaire for their application. Lighting control is one of the easiest ways to improve energy efficiency, therefore careful consideration should be given to the lighting control. The type of lamp, ballast, switchgear and control gear should be taken into consideration when applying lighting controls. Alright. There's a note there. To operate lighting only when and where needed, permanent control of lighting may be implemented by use of, for instance, movement sensors, dimming controls, time switches, clocks. Yeah. But now, now we have to actually consider it and document it. Heating, ventilation and air conditioning. Consideration should be given to the choice of HVAC equipment depending on the installation structure and usage, and the appropriate control system to optimize environment control, temperature, humidity, etc., depending on the usage and occupancy of individual spaces. Okay, distribution systems. Efficiency of a distribution system is based on the following. We have intrinsic efficiency of electrical equipment such as transformers or reactors and wiring systems, and topology of the electrical distribution system at all levels of voltage, for example, the location of primary transformer and length of cables. Transformers and reactors, where one or more transformers are used to supply the installation, special care will be taken concerning the type and its efficiency. Okay, yep. Wiring system, the cross-sectional area of conductors and integrated architecture may be optimized to reduce losses. To optimize integrated architecture by locating the power source at an adequate location and optimize route of wiring systems to put the source closer. To reduce losses in the wiring by increasing the cross-sectional area of cables compared to the minimum sizes provided by 60364 and or reducing reactive and harmonic currents, regulation 6.5 shall be applied. Okay. So yeah, considering thermal losses that are created by having cable sizes that are carefully selected, we now need to reverse that thinking a little bit, say, okay, now we've done that, let's actually then consider energy losses, let's increase it again a bit more. How much more doesn't really, unless we're going to start taking thermal data, which you can do if you've got the cameras and stuff for that. Power factor correction. Reduction of reactive energy consumption improves electrical energy efficiency as maximum electrical energy will be transformed into active energy. Reduction of reactive energy will also reduce thermal losses in wiring systems, particularly in the low voltage public distribution system, and reduce energy losses in the high voltage transmission, high voltage distribution network and the customer's network. If you know anything about power factor correction, then That's obvious. That's why you do it. Installation monitoring systems. The electrical distribution system needs to meet the monitoring capability requirements. In the case of measurement by zone, each zone shall have a dedicated feeder, allowing an installation monitoring system to perform the relevant measurement. In the case of measurement by usage, each usage shall have a dedicated feeder, allowing the installation monitoring system to perform the relevant measurements. Okay. If I'm skipping some of this larger, just pause the video. It's just you're going to get more bored if I have to read everything. Alright, an installation monitoring system shall have three main objectives. First one, control of performance and benchmarking of consumption pattern. So an annual measurement of the total kilowatt hour consumption based on utility meters can be used. Time data measurements, such as every 30 minutes, can also be used. What's the other one? The identification of energy use and any changes of consumption pattern is also necessary. I mentioned this earlier on. So build an action plan and check the effectiveness of actions, and check the operation of control systems used to optimize consumption. Changing in demand, changing in use may affect this. It may need to be checked. Power quality surveys. Power quality may influence energy efficiency performance in several ways: extra losses or abnormal aging of equipment. If you've done any power quality analysis, or you have the instrumentation for that, there's a no market for that. All right. 801.10.2.3.2 801.10.2.3.2 energy. Okay, it's of prime importance in terms of electrical energy efficiency to ascertain or determine by either calculation or measurement the energy consumption of each item of current using equipment. Load profiling. Measurement of the energy used over a short period of time is necessary to give a load profile. This should be over a period of minimum 24 hours to give a reasonable estimate of load profile. If you've done any maximum demand calculations where you've actually looked at a profile of load, there's even an illustration of that, I think, in the electrician's design guide. This is load profiling, looking at the load for a 24-hour period and actually then deciding how to change the characteristics of the system, how to heat the water at night time instead of heating it at the same time as this other equipment. Try to recognize the different loads and time their operation at a place where the overall demand is brought down and they're all kind of collecting together. That's simple load profiling. Voltage drop has an impact on electrical energy efficiency of the electrical installation. Where the voltage drop measurement is required, the installation voltage measurement shall be made on the current using equipment at the origin of the circuit powering the current using equipment. Power factor. Where power factor measurement is relevant, it shall be implemented. Okay. Harmonics. Non-linear electrical equipment such as power electronic systems, including power drive systems, inverters, UPS, other power converters, arc furnaces, transformers, discharge lamps, blah blah blah. Harmonics provoke overheating and as a consequence generate additional power losses through the wiring system. Therefore, the measurement of total harmonic distortion of voltage at the installation level and total harmonic distortion current at the current using equipment level for harmonics is recommended. Appropriate measurement for other harmonics should also be performed. If you've got equipment that can do that with your power analysis, then brilliant. Otherwise, you can calculate some of this data if you've got accurate demand data. But yeah, that is all of 801 up to the Annex. So the next video is going to be the Annex. The Annex is going to have the calculations used for. There's a couple of parts of it. One is for. Positioning here, one is the barycenter method, which will go to this here. So we'll use that formula, and we'll look at some numbers, and we'll see the conclusion. And the other part of the Annex will just be observing the tables that are in the draft. There are tables all done to select criteria to then put into an energy efficiency performance, and we'll see how that is going to work down the line. But to summarize this, I mean, we've done energy efficiency consideration over the past 10 years. New technologies, LEDs, sensor switching, It's already been coming and it's been introduced, so a lot of this is kind of done already. It's just a case of recognizing that that is there, and then moving on to proving it with documentation and calculations if you need to. But similar with this, we've been doing this for a while now, but now there's regulations telling us to do this. What we need to get used to is these terms, though. Load profiling, meshes, the barycenter. These are probably new terms that we've not used before in our normal designs, but I don't think that's going to be a big problem. There's a bit of guidance with this, and again, I'll put another video on which will cover the barycenter calculations as a good example. But download the IET wiring matters. They've gone through this, and a lot of it is, don't worry, it's going to be fine. And to be honest, it's true. There's a lot of words here, but when you actually chew through them, it's stuff that in industrial work, especially, we've been doing. So it's not a significant problem. I will start working on a second part to this, the Annex Part 8 video, which I will upload as soon as that is ready. But if this is brought in, it may not be brought in. They may decide to pull it out, because again, we've been doing a lot of this. They could sprinkle some of this through the rest of the book instead. But if they do bring it in, other than a couple of new terms that may have to be put aside in our design, it's not going to be a significant thing, so I won't worry about it. I will see you in the next video, which will be Annex 801. See you there. Bye bye.